Topic of today's research seminar is labeled optimal partitioning. And I'm going to, there's like 60 slides or something, but they're going to go pretty fast. So yeah, I expect to finish in about like 35, 45 minutes. So hopefully we'll have some time at the end for discussion, but feel free to stop me in the middle with this questions as well, okay?
I have a question before you start.
All right.
I signed up for next week's, and I haven't made a presentation on that topic yet, but it's really interesting to me. But what's the kind of length you want? Because I'm just wondering how much I can scrap together and rehearse for next week.
30 to 45 minutes is good.
All right, I'll shoot for that.
Yeah. And so, yeah, thanks for doing that, Joe. We'll talk about the future presentation schedule after this, okay? So yeah, I'm gonna get started here. So I divide my talk into 4 sections. Section number 1, introduction, supervised change point detection for cancer diagnosis with DNA copy number data. So this is going to give some motivation as to why this algorithm is useful and hopefully applicable to some real world hard-hitting medical problems. Then after that, I'm going to talk about the new algorithm called labeled optimal partitioning. And I'm going to give a detailed demonstration of how the algorithm works for a data set. And then I'll discuss some results figures and some future work. So the motivating problem for this research project is cancer DNA copy number analysis. And so I guess you guys probably haven't heard about this stuff before, so I'll give you just kind of like a brief overview. So usually, in every one of your cells, you should have something that looks like this. And so basically, this is a spectral karyotype where you see all of the different chromosomes in different colors. And if you have a normal cell, you have 2 copies of every chromosome. One came from mom and one came from dad, right? Except for here in the sex chromosomes, one came from mom over here and this one came from dad, right? And so what we see is that in a normal cell, you see something that looks like this, where everybody is present in exactly 2 copies. And in the cancer cell, you see something that looks like this, where sometimes you can have chromosomes present in twice as many copies. Sometimes you can have big chunks of chromosomes that are glued to other chromosomes. Like for example, here it looks like maybe a chunk of chromosome 2 has been glued to a chunk of chromosome 17. Right here, you see a chunk of chromosome 10 being glued to a chunk of chromosome 12, right? So there's lots of what we call copy number alterations, where you have the different parts of the chromosome present in different numbers. And so this can be very useful in diagnosing cancer. And so this is the main motivating problem for this kind of research. So to give you further motivation about why this kind of problem is interesting, I make this figure where, I'm showing you basically like how this copy number is measured in practice these days using these kind of high throughput data DNA microarrays or sequencing techniques. And so basically every one of these rows going from top to the bottom is a different patient. And what we're plotting for each one of those patients is this log ratio on the y-axis as a function of position. And the log ratio, it's like a rough measure of copy number. So when the copy number is hovering around 0, like we see for these 2 chromosomes, that's about the normal level. When it's above 0, that indicates that a chromosome is present in more than 1 copy. And then when it's below 0, like this guy over here, you can see that means that there's been a loss. So there's the part of, or the whole part of chromosome 3 here, which is present in less than normal copy number. So maybe 1 copy instead of 2. And so what's interesting about these data is that they can be used to diagnose cancer. So if you look at these labels on the right-hand side of the plot, do you guys see okay, relapse, relapse, relapse? Do you guys see that?
Yeah, it looks good.
Yeah, so now the question for the audience, very briefly, is can you come up with a classifying function that takes all of these noisy data as input and is able to predict whether or not the person is going to be okay or relapse? So the okay patients recovered after their initial treatment and didn't have any more cancer. whereas the relapse patients, the cancer came back. And so it'd be interesting to know if we could figure this out just by looking at the data diagnosis, right?
I have a question.
Yeah.
So on OK11, on that row, on the very left, the y-axis is different. Why is that?
Yeah, so actually all of the y-axes are different. So I plotted all of the y-axes such
now I
that every
noticed.
profile has its own scale, right? So
Does that just depend on the data?
yeah, the different data sets are going to have different scales, yeah, but the general rule of interpretation applies. You know, if it's hovering around 0, that's normal, but if it's above or below, that's more or less than the regular number of 2 copies.
Yeah, because I've seen this figure before, but I never noticed that the y was.
So any ideas about, you know, a classifier to predict whether or not the person would be okay or relapse? So what do you see in the relapse profiles that you don't see in the okay profiles?
A lot of them are below 0 and above 0 in the relapse.
Yeah, a lot of them are below 0 and above 0, but also you see that in the okay profiles too, right? So here, this one is quite a lot above 0. This, you know, you have some which are below here. So I don't know if that one would really work for really distinguishing the two.
So for me, when I look at relapse, the changes from the normal, like the previously established values, are really abrupt. And there's certain sections that deviate from 0, but it's very abrupt like that. Versus the top, it's mostly consistent, at least far more consistent than the bottom.
Yeah, so Joe noticed something about abrupt changes, right? And so actually that's kind of the pattern that people use usually to make this kind of diagnosis. And so you can see that clearly here, like for example, chromosome 1 in this relapse patients, you have an abrupt change from below 0 to 0. In chromosome 2, you have an abrupt change from above 0 down to 0 and then back down to below 0. And so you don't usually see these abrupt changes within chromosomes for the OK patients, right? So here you see a patient that's just got a noisy profile, but you know, if we're interpreting those things as just noise, then you know, we would say that all of these guys are just flat chromosomes. Whereas, you know, down here, you can see there's abrupt changes within the chromosomes.
I have a question.
Yeah.
So once again, OK11, that very first cell to the left, there's that part that hangs down, but are we still considering that noise because it goes back to 0? Or what would that be?
Yeah, that's a good question. Maybe if you saw that by itself, you might conclude that that's a significant change up, right? But looking at the rest of the profile, you see that there's quite a lot of, you know, noise up and down. So, you know, we might conclude by looking at the rest of the data set that maybe there was just something noisy happening on measuring that guy's profile, right? So,
yeah, but it still looks different for relapse.
Yeah, so yeah, I mean, all of this to say that, you know, with these relapse profiles, you know, one of these indicators for predicting them is the presence of these abrupt changes within chromosomes. And that's going to be like kind of the main motivating application of the algorithm that we propose. We're going to be able to have an algorithm that is going to be able to accurately detect these changes within chromosomes. And so we're going to be able to more accurately diagnose whether or not these patients will have this, you know, more aggressive relapse form of the cancer. Does that make sense to you guys? Any questions about that?
That makes sense to me.
Sounds good. All right, so going on, you know, in previous work, we proposed this SegAnDB interactive machine learning system. And so here's a figure 1 from my paper in 2014, where, you know, basically in this system, the user is going to upload a bunch of noisy data sets like the one we were just looking at for machine learning analysis. But then the user can also provide labels which indicate presence or absence of change points in specific regions of data sets. And so what's interesting and novel about that is that then the machine learning algorithm can use those labels in addition to the raw data for predicting where the change points are. So in the figure, you can see these yellow regions indicate a region of the data where the user has said there's no abrupt changes, and the red regions are regions where the user has said that there's exactly one breakpoint or abrupt change in the region. And so the machine learning system then uses those labels and then gives the user a model which is consistent with those labels that have been given. And so the model that is used on that system is one of two here. Either the classical optimal change point model, which is a maximum penalized Gaussian likelihood. And this model is used if one of those models has zero label errors. And this is implemented in the Opart optimal partitioning algorithm described by Jackson et al. In 2005. And it also can be computed by this faster FPOP algorithm proposed by Maidstone et al. This is one of, I was co-author on this paper back in 2016. Both of these algorithms compute the same optimal change point model. And it works most of the time, but there's some cases where it doesn't work, which we're going to see in a little bit. But anyway, when it doesn't work, we can use this label-aware Segano algorithm, which we proposed in 2012. And it's always guaranteed to have zero train label errors. So it's always guaranteed to have change points that are consistent with the provided labels, but it never predicts any change points outside of the positive labels. So that can be really annoying if you have a big data set and you would have to label all of the changes in that big data set in order to get all of a model with all of the right change points. So to give you an example, here's a simulated data sequence which kind of explains why these two previous algorithms are not good enough. So again, the plot is some signal versus position. Here I'm just taking 100 data points. And the idea is that in addition to these noisy data points, we also have these labels. And so here in this paper, we only consider 0 and 1 labels. So the 1 labels mean that we want exactly one change point in that region. And so we have 2 of these labels. So we want exactly one change point somewhere in here and exactly one change point somewhere in here. And then the 0 label here in orange means that we want no change points in this region. And so this also illustrates a typical use case for the labels. So here we have kind of like a slight change up, which maybe not is so easy to detect unless the user labels it and tells us that it's actually a significant change. And here we have kind of a single outlier jumping up and then the signal jumps back down. And we've put a -0 label to indicate that that's just noise and we don't really want a model that's actually having change points in there. So, so is there any question about that example data that we're going to analyze?
I'm a bit confused about the change point in the middle. I can't really see it.
Yeah, well, that's a good question. So the question is, why is there this change point label in the middle, right? And so, maybe you can't see it obviously, but that's kind of the whole point of the labels actually. If for some reason you have, some other reason to believe that there should be a change point in these positions, maybe there's a gene in that position, maybe in some other samples there's also a change up in that position, there's a lot of different reasons why you might expect a change there, and you might want to actually have the model detect it even if it's a slight change, right? Does that make sense? Did that answer your question?
You're muted, Joe.
Sorry, I was muted. So you're basically saying that position 50, and this is for one chromosome, right?
Yeah, this is a simulated data set, but yeah, you can think about one chromosome.
Yeah, okay, conceptually, but you would think that 50 would have a change, and you have it there because that's where you're expecting it to be.
Yeah, so it's kind of a way of bringing prior knowledge to the table in interpretation of your data set.
Okay.
So going on, here I'm going to show you a bunch of models where you have a different number of changes. This is the optimal partitioning algorithm with, so it's got a penalty parameter that controls the number of change points which are detected. And so here the penalty here is lambda equals 1,000. And so that when you have a really big penalty like that, you get a model here which is totally flat and there's no changes at all. And so when there's no changes in these one labeled regions in red, we call that a false negative, right? Because we want to change somewhere in there, but we're not detecting one. So that's an error that's a false negative error. So if we play with a penalty though, we can find an Opart model which starts to get a change here in this left red region. And so in this case, this model with penalty equals 100, we have only one label error, one false negative here. And so it's doing a better job than that first model because it's detecting this change right here that we had labeled and that we wanted to detect, right? And going on, here we have a model with a penalty of 20, a penalty of 15, penalty of 10. And so starting at a penalty of 10, we start to get a jump up and a down here in this negative labeled region, right? So this negative label, it says, hey, we don't want any changes in this region. And when the model is detecting a change up and down here, we call that a false positive, right? So that with the dark black border, that's a false positive. And so, we can keep going, and eventually, when the penalty gets small enough, you have a penalty of 5, and you start detecting 2 changes here in this red region where we know based on the label there only should be 1. So here that's also a false positive. So this is even worse. And if you keep going, even smaller penalty of 4, you start to get several changes in the second region. So that's interesting. So you keep playing with the penalty going from a very large value to a very small value, and for some reason you're never able to get a model that gives you a change point, exactly one change point here. Either you have none or you have more than 1. So here's an example of a label where you're never able to satisfy, or you're never able to find a consistent model with this classical Opart approach, which ignores these labels and just uses this penalty. And here, this is what happens when you use a penalty of 0. If you're curious, it just detects a change point everywhere. And so the other algorithm that I said we used in this existing system is called Segano. And what it does is it has, it finds the most likely change points that occur such that there's exactly one change point that occurs in each red or positive labeled region and no changes elsewhere. And so this is a good model, with respect to the given labels, but it's kind of annoying because it's not able to detect some other obvious changes. Like for example, here you have a big change down from about like 7 or 8 to about like 5, right? But it's never going to be able to detect this change down unless you manually provide a positive label there. So that's kind of the drawback of the Segano algorithm. It's good at fitting the given labels, but it's not good at predicting new change points at unlabeled regions. So are there any questions about the drawbacks of the previous algorithms that we've been using?
I have a question.
Yeah, sure.
So that 0 label, you put that, you don't want a change point there because that's corresponding to that one data point around position 80 that's way above at signal like the value of 10.
Yeah.
But you didn't put a label for like right at position 75, even though that's a pretty obvious change point.
Yeah, so the question is, we have a label at the end, is 0 label, but we don't have a label at position 75 for this pretty obvious change down. And the answer is yes, that's exactly right. So, the user may not have enough time for whatever reason to have given labels in all of the places where there are even obvious changes. So,
okay.
So yeah, that's one of the key assumptions of this method. We have a partially labeled data sequence. So we have labels in some parts, but the user doesn't have enough time to give us labels in all of the data set.
So it should still be useful, even if not every single change is labeled.
Well, yeah, that's the idea, right? So in this data set, I mean, even though it's not labeled here, we would still like to have a change down. And here it's kind of like a contrived example, but sometimes you have data sets which are, you know, maybe hundreds of thousands of data points long. And, you know, there could be maybe dozens or hundreds of changes, right? Do you really want to have to go through and label all of those?
Yeah, it doesn't sound like too much fun.
No, I mean, that's the whole point of machine learning. It should be able to figure out what you want just based on a few labels, right?
Mm-hmm. Okay, thanks.
Yeah. Anything else before we go on? Okay, so yeah, that was kind of the introduction section. And so yeah, to recap, you know, the algorithm that we're proposing is useful for DNA copy number analysis, and we've shown, you know, these two previous approaches and why they're not good enough. So, you know, that's actually a pretty good approach to use in any of your talks. If you're going to give a talk in this group or in any kind of academic setting, it's always good to start out with kind of, you know, the big picture, you know, why what you're working on would be useful to someone in the world. And second of all, you know, why is existing work in this direction not good enough, right? So we've given an example of why these two existing algorithms are not good enough in this particular simulated data set, right? So to solve these problems, we're going to present this new algorithm called labeled optimal partitioning. And so to explain what the algorithm is doing, we're first going to explain what the regular, you know, the Opart optimal to partitioning algorithm does. So this is the previous algorithm that we've seen that has this penalty. And to describe exactly what it's doing, well, you have to assume that your sequence of n data points is this vector bold x, which is x1 to xn. We're going to assume we have some loss function that we can use on these data. So for the data that we've been looking at, we're going to be using a square loss. But, you know, for other kind of data, we can use other loss functions, and this approach works just fine. I is an indicator function over here in this objective function, which is going to be measuring the number of changes. And we're going to assume that we have some non-negative penalty. Remember, this is this parameter that controls how many changes, right? So if you have a large penalty, you have fewer changes. So this algorithm computes the optimal solution to this this problem, where here we want to find a vector m of n real numbers, which minimizes the following cost function. Here we take the sum of the loss over all the n data points. So this is the loss of these m values with respect to the x values. Again, the x are the raw data, and the m, this is going to be the mean that we've seen visualized as the kind of like mean line in the previous pictures. And so what this algorithm is doing is minimizing this loss plus this penalty lambda times the number of change points. Here, this indicator function of when the mi is not equal to mi plus 1, this measures how many times there are abrupt changes in this mean vector m. And so the key insight of the Opart algorithm is that you can rewrite this minimization over all of the n segment mean variables in terms of a minimization over just the last change point variable tau. So here we're writing this minimization. So the tau takes values between 0 and n minus 1. So these are all of the possible places where you could put the last change point. And the key insight is that we can rewrite this complicated cost in terms of this optimization over just this one change point variable. So once we've computed all of these n possible cost values, we just take whichever one is minimum, and that's going to give us the best change point model. So again, tau is the last change point optimization variable. C hat tau, this is the optimal cost computed at the previous iteration of the dynamic programming algorithm. And L, this term over here, it's the cost of the last segment. So this is the segment between the last change point tau plus 1 and the last data point n. So it's maybe seemed a little bit abstract, and you know, this is the way to describe it if you really want to know exactly what the algorithm's doing. And if you want to know a little bit more details, you can go see our archive paper, which I have linked on the group webpage. But yeah, I'm going to explain what the algorithm does in pictures now too. So the idea is that here I'm showing you the same kind of data set. So these data plotted in this top panel are the same data set that we were looking at before with these two labeled positive changes. So there's two positive labels and one negative label. And so what I'm going to be plotting here in the bottom panel is the cost of the last change. So for all of the different values of that tau last change point variable, I'm going to be plotting what the cost is. And so basically what this algorithm is doing is it's kind of recursively computing the optimal cost. So here I'm starting out at the very beginning of the algorithm where if we're just computing the optimal cost up to data point t equals 2. Here I've rewritten the recursion that we saw in the last slide in terms of w's, because that's a notation that we use in the paper instead of the c's. But the idea is that here the optimal cost up to a data point t can be written in terms of this minimization of the last change point variables tau, and where you have three different terms, where the first term is the optimal cost up to some previous change point tau. The next term is a penalty lambda. And then the last term here is this optimal cost of the last segment. So to give you an idea, if we're computing just the optimal cost up to the second data point, there's only two options to consider. Either at tau equals 0, we have no changes, and the last, the segment, it goes over all the data, the two data points. Or if tau equals 1, this means there's a change point after the first data point. And so there's one change point between those two data points. So this seems pretty silly, but this is the kind of the simplest example, of this equation that we're solving. And so you see the cost values here. So it says tau star 2 equals 0. And so what it means is that here, after looking at these two options and considering the penalty value that was given here, I'm giving an arbitrary value of 10. What we can see is that the better option is the one with the lower cost is this first one, right? So this first one has a lower value and the second one has a higher value. So if we have to choose between the two, we choose this one with no change point. So going on, if we go to what's the best model up to 3 data points, here now we have to search over 3 possible tau values. So here, tau equals 0, again, is the model with no changes. Tau equals 1 is a model where the last segment ends after data point 1. It starts after data point 1. And then tau equals 2 is this model that the change point is after data point 2. The last change point is after data point 2. And so here's already you can see the recursion coming into play. So remember when we computed the optimal cost here up to t equals 2, we compared these two options, right? And so at this point, we did this optimization and we saw, well, actually this model is better. It's more optimal. So we already know that up to data point 2, this is the best possible model. So now after going to data point 3, we already know that if we have a change point here after data point number 2, we already know what the best model is on the previous 2 data points, right? Because we already did that optimization in the previous step, right? So for these 2 previous data points, we don't have to consider anymore a change between those data point 1 and data point 2, because in the previous step, we already computed that and we discarded it because we saw that the model with no change is less costly, right? So that's the essence of dynamic programming. The idea is that if we've already computed something here, we've computed the best model up to 2 data points. We can just use that cost, and that's what this W tau term in this optimization here represents. It means it's this optimal cost up to a previous data point tau that we've already computed in a previous iteration. And so, anyways, so for
I have a question.
Yeah, sure.
How is W tau what's the difference? I'm still not visualizing, like, what is that different from L, like that third term in the equation, the optimal cost of the last segment?
Yeah, so good question. So the W tau, this is the cost up to tau. So that's the cost up to 2 here, if tau equals 2, right? But the optimal cost of the last segment, the L here, this is just the optimal cost of this last segment, which is just hugging this last data point at 3, right? So it's a little bit trivial here, but we'll see some more interesting examples as we go on.
So like for that given model, the last segment in the model is that one at the third data point. So that's what it's referring to?
Yeah, that's right.
Okay, that's much better.
So going on, so I'm skipping a bunch of steps here. We're going up to t equals 25. So at this point, how do we figure out what is the best model up to t equals 25? Well, we do this optimization again, considering all the possible change points. We consider the tau equals 0, that's the cost of the model with no changes. Tau equals 10, that's the cost of a model with change after data point 10. And then, you know, what we've already computed in previous iterations that model had no changes. So we use that cost already. You know, tau equals 19 here, which is the change point right before we get into the one labeled region. And then finally, we start to consider all of these other changes inside of the labeled region. And what's interesting here is that you can see now that there's a difference between the algorithms. So the cost values here in blue represent the cost of the usual Opart algorithm, which will just optimize over all of the previous possible change points, right? Even the ones in the red region. But so with the new Lowpart algorithm that we propose in black, you see that these black triangles are gone down here. So what it means is that the Lowpart algorithm, if you want to compute the optimal cost and guarantee that there's exactly one change in these red one labeled regions, that means that during these optimization steps where t is inside of one of these one labeled regions, you have to discard the possibility of the last change point being inside of that red region that you're considering. So that's maybe not super interesting, because I think the best option here was maybe still the first option here with tau equals 0. You see it's quite low cost for both the algorithms, so it doesn't make a difference here in this case. But if you go on and we're trying to compute the best model up to t equals 51, well, here you don't see a difference either. So here, let's consider the options again. Here at tau equals 0, again, this is a model with no changes. Going to tau equals 10, here's a model with, you know, the change point after data point number 10. And here what we see is that, again, there's going to be a difference in the optimization between the Opart and the Lowpart. So here we see that there's no black triangles at this part of the plot, which means that the Lowpart algorithm is not going to consider that it's possible to have a change point before this tau equals 20 point. And so that's going to enforce the constraint that there must be a change point in this red region, right? So it's definitely possible with the Opart algorithm to not have a change point in this red region. But to enforce this constraint with the Lowpart algorithm, what we do is we discard the possibility of having this last change point being before the previous one labeled region. Anyway, going on, we see that both of the algorithms, they take a minimum cost at this tau star 51 equals 25. So that means if we're computing the best model up to data point number 51, well, after looking at all of the different possibilities, we see that, well, the lowest cost possibility is this one, where the change point is right smack in the middle of that previous one labeled region. And so again, there's not a difference in the optimal change points that are computed yet, but here we're going to see a difference. So going up to data point number 75, what happens is that here we, again, we're optimizing over previous change points, but here with the previous algorithm, the least costly change point happens to be just before the one labeled region, right? So here you can see the last change point here happens just before this positive label, whereas for the for the Lowpart algorithm, again, we're discarding the possibility of having a change point before that previous one labeled region. So it's not able to consider that as an option because we want to enforce the constraint that there's a change point in this one labeled region here. And so instead of picking this as the minimum, which is actually less costly, it's not allowed to because it has to enforce this constraint. And so instead it picks this change point at data point 51. And so then you get two different models as being the best up to data point number 75. Going on, you know, the other thing that you have to consider when you're implementing this algorithm is that if you're considering, you know, computing the cost inside of one of these negative labeled regions, using the traditional Opart algorithm, it just ignores all the labels. So it's going to have to compute all of these cost values. And whereas with the Lowpart algorithm, we know that there could never be a change point at this position. So we can just completely discard this and not even compute the optimal cost at this position. So that's what I'm drawing here in the bottom panel by showing you no black triangles. Finally, if we're computing the complete model up to 100 data points, so this is the model, the model that we want to compute for the entire data set. How does it work? Well, we have to compute the best cost using the same recursion. Here with t equals 100, we search over all the previous possible tau values, and you notice that with the blue previous Opart algorithm, there's 99 previous values, right? Every one of the previous possible change points must be considered. Whereas with the Lowpart algorithm, well, you only have to consider the guys going up to the previous one labeled region and not including any of the zero labeled regions. You see there's no black triangles in the zero labeled region here. So the result is with Lowpart, you get a model that looks like this, where there is a change in these two red regions, and you also get a change in this black region here. In this unlabeled region here, but you get no change in this zero labeled region. Whereas with Opart, you get something like this. The optimal model looks like, well, it's not got a change in this red region here, and it does have these changes in the negative zero labeled region here. So yeah, I mean, all of this to say that we've kind of discarded a bunch of possibilities in our update rule. And so what this amounts to doing is just playing with this set t sub t, which basically is the set of previous change points that we're optimizing over. So with the classic Opart algorithm, we consider all of the possible previous change points, which are these blue circles. But with the Lowpart algorithm, all we have to do is throw away a few of those previous change points, and then you end up with these black triangles. And that'll get you a model which is consistent with the labels and optimizes the cost. So yeah, I don't want to go into too many details, too many more details about the exact equations which are used, but this is the main result of our paper. You can use this update rule to compute the optimal cost. If you want to see the proof, it's in the paper. The other thing I wanted to mention here is there's an interactive figure that I made, which is a kind of more complicated version of the previous figure that we were just looking at. And you can pull that up. It's also linked on the group webpage. And so if you pull that up, you see that you have these three different plots which are linked to each other. And on the top plot, you get to kind of navigate through the different t and the different tau values like we were doing in the slides. So if you want to kind of explore at different values that I was not able to show you in the slides, you can do that yourself here. And you can see what the different models look like. And you can notice that the other plots are updating as well, right? So if you go look down here, you can see this black dot and these gray lines updating. And so the black dot represents the last change. And then the gray line represents the last data point that we're considering. And you can also navigate through the data by looking at this. And so what you can see by looking at the difference between the Opart and the Lowpart cost here is that with the Opart algorithm, you have to compute this whole triangle of cost values, right? So you can see how it can get really, really large, really fast. With a large data set, it's obviously a quadratic time algorithm because you have to fill up the whole lower triangle, right? However, with the Lowpart algorithm, you can see that with the blank or white parts, we don't have to actually even compute them at all, and we still get the optimal solution. So these big blank spots here correspond to the 0 labeled regions, right? And these kind of other blank spots over here correspond to regions of the parameter space that we don't have to explore because of the 1 labeled region. So the moral of the story looking at this picture is that, the Lowpart algorithm is actually a lot faster too, because we don't have to compute a lot of the things that we do in the original Opart algorithm. One last thing about, yeah.
Go ahead. A quick question, just more in general, what do you use to create all these interactive data visualizations?
Well, here I use the Animant package. It's basically an interactive version of ggplots.
Okay.
And you can see all the code. It's linked to on the group web page if you're interested.
Yeah, because I wanted to try it out.
Last thing about this figure is you can also change the penalty. So if you use a really low penalty, you'll see that the optimal model at the very end has a lot of change points. You see lots of changes here. And if you use a really large penalty, you'll see the optimal model is going to have only changes in the 1 labeled regions and no changes anywhere else. So yeah, there's still a penalty parameter in this new Lowpart algorithm. So going on, we're just going to have a little bit of discussion of the figures from the paper, which summarize the main results here. This figure shows the computation time of these different algorithms as a function of the number of labels. And here we show that the empirical time complexity of Lowpart gets to be very fast when you have a lot of labels. So with a very few number of labels, it's about the same computation time as Opart. But with a lot of labels, it starts to get just as fast as this FPOP algorithm, which is a really fast way of computing this optimal segmentation. So that's good. That's really interesting. It's actually can be even faster than the previous Segano algorithm when you have a lot of labels. The other time analysis that we did is we looked at computation time as a function of the number of data points. And so we can see that the previous Opart baseline in blue is quadratic time. So it means it's got this bigger slope on this log-log plot. And in contrast, when we have here in both of these experiments, we're having a constant label density. That means the number of labels is proportional to the number of data points. So as we get more data points, we're also getting more labels. And in this scenario, we're seeing that all 3 algorithms here, Lowpart, FPOP, and Segano, seem to be log linear. So quite a lot faster than the previous Opart algorithm. And furthermore, when you increase the label density, you see that Lowpart gets to be quite a bit faster than Segano. So that's consistent with the previous figure that we showed. And kind of surprising, because you see it's actually faster than FPOP in some cases where you have lots of labels and lots of data. So in this figure, we see that we're comparing the number of training and test label errors between Opart and Lowpart. So on the x-axis, I'm showing you the number of train label errors, and on the y-axis, I'm showing you the number of test label error differences. So so what this means is that here I did some cross-validation experiments in a bunch of different labeled data sets. And so for example, here it says that in 685 of the different data sequences and splits, there was no differences between the 2 algorithms. But in a bunch of cases over here, on the right side, that means that Opart has some train errors, whereas Lowpart has none. And on the top above the 0, we see that the difference between Opart and Lowpart in terms of test errors is sometimes positive. So that means that sometimes Lowpart is actually better in terms of test error than Lowpart. And notably, you don't see anything below the 0 or to the left of the 0. And what that means is that in the best case, that means optimizing over all of the possible penalties, we can always find a Lowpart model which is as good as Opart. So there's no data sets that I analyzed in which Opart gave a better result in terms of train error or test error. So that's a really encouraging result. And we did the same kind of analysis with Segano, but here we're dividing it into true positives and false positives. And the reason why we do that is because in both of the Segano and Lowpart algorithms, they both always get the number of errors in the train set equal to 0. And so this is a comparison in terms of test errors, right? So what this says, again, this gray line here, this represents the equivalence between the two algorithms. So it says that in 282 data sets, there was no difference. There was no true positives, but also no false positives in both of the algorithms. And so similarly, going along the diagonal, that's when there's 1 and 1 and 2 and 2, right? But you see that there's all of these guys on the right side of the diagonal or below the diagonal. And these are examples of data sets where Lowpart has true positives, but so it has more true positives than it has false positives, right? So what that means is that it's actually got, it's doing quite a better job in terms of test errors in quite a lot of data sets, right? So you see there's a big concentration. Here are 419 examples with Lowpart having 1 true positive, but no false positives. So that's pretty good. And so here this figure explains, again, some test accuracy. We did some cross-validation experiments where we have you know, some labeled data sets as a train set, and then we have some other labeled data sets as a test set. And we're trying to learn a model using various different algorithms and penalties. And so the different algorithms are represented by the different symbols, the different colors here, and the different penalties. Here, I'm not going to go over all the details, but you know, here we're using 3 different penalty learning strategies. Here, the big strategy has 0 learned parameters. The constant strategy has 1 learned parameter, and the linear strategy has 2 learned parameters. And using all of these different penalty learning strategies, we see that the test accuracy has the same kind of trends across 2 different test folds. These are the 2 different panels here. And across, so the trend that we see is that Segano tends to have the lowest test accuracy, and that makes sense because it's not predicting any changes in the test label, so it's got a lot of false negatives. And then we always see that Opart is doing quite a bit better than Segano, and then Lowpart is doing slightly better in every case, right? So those are pretty consistent trends across all of the 3 penalty learning strategies that we tried. And so again, that's a really encouraging result for this new Lowpart algorithm. It says that, you know, if we want to use an algorithm, we should use Lowpart because it's better than both of the previous baselines. And so the last kind of analysis that we did in the paper is the analysis in terms of rock curves in cross-validation experiments. So kind of similar to the previous figure, I have plotted the different penalty learning strategies in the different panels going from left to right, and then the different test folds in the panels going from top to bottom. And here every algorithm is represented by a different rock curve or dot. So with the Segano algorithm, this corresponds to 0 false positive and 0 true positive in every test set because it's never predicting any change points in the test regions, right? And it doesn't have any penalty parameter to vary, so it's just one dot right there at 0, 0 instead of this whole line. So the Lowpart and the Opart algorithms are drawn as these blue and black lines because they have this penalty parameter, and so varying the penalty parameter between a very big value and a very small value gives you these rock curves. And the dot that we draw here is the dot that represents the predicted value. So at the learned penalty, you know, we see that you know, the false positive and the true positive rates are given by the plotted dots here. But what you see across all of the different test sets, experiments that we looked at, we always see that Lowpart has slightly better AUC. So it's all, when you're looking at this rock analysis, if you've never seen this before, it's always better if you have a rock curve that's going up right away and then over. So if you're having a rock curve that's higher, you get more area under the curve, and that's this AUC number that we're plotting here. And so you see that consistently across all of the data sets and penalty learning strategies, you see that you've got slightly larger AUC with the Lowpart algorithm compared to the Opart algorithm. So that's you know, another indicator that the Lowpart algorithm that we propose is quite useful and should be preferred in practice. So yeah, to summarize, the algorithm that we propose fixes issues with the two previous algorithms. So it's got better train and test accuracy. And our results demonstrated an improved speed and accuracy of the algorithm. So we have an R package published on CRAN called Lowpart. And the code that was used to create all of the figures and the slides in this presentation are also on GitHub. And so for future work, and maybe we can talk about this offline with some of you if you're interested to working on this, because I don't have anybody working on this right now. But we could think about making a functional printing algorithm, which is similar to the proposed Lowpart algorithm, but it should be able to solve more complex constrained change point problems. So instead of having labels that say there must be one change in some direction, you know, the labels might say that the change must be non-decreasing or a change up. And we can actually have an algorithm that enforces that. And it should be faster.